The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
We'll look here first at exothermic reactions, and we'll contrast that with endothermic reactions. An exothermic reaction starts at reactants and it releases energy and it goes to products. And that's because the reactants initially had a higher amount of energy, and then the products here will have a lower amount of energy. Now, in contrast with endothermic reactions, the reactants begin with a lower amount of energy, so they have a lower energy profile, and they end up with a higher energy. They end up with a higher energy state here, and energy therefore is going to be absorbed. Okay, great. Now let's take a look at the energy in each phase. We'll start here with the exothermic reaction. With the exothermic reaction, let's say our reactants here have no unpaired electrons. Therefore, the two reactants will repel each other. And if those two reactants are repelling each other, they're going to need a specific amount of energy to get over that repulsion if they are to react. And that energy is kinetic energy, and it basically comes from the collisions. Now, once it has enough energy, that kinetic energy will become potential energy in the transition state. That potential energy is then transformed back to kinetic energy in our products. So the AC and the B products. Wonderful. Now let's take a little bit of a deeper look here at the transition state. During the transition state, so at one point, the A and the B bond is going to be partially broken, and the B and the C bond is going to be partially formed. So at one point, yes, all reactant A, B, and C are all weakly connected. Great. Now, if we see here, this right here is the activation energy, or the energy hill, whatever you want to call it. And what is the activation energy? Well, let's take a look at our definition down here. It's the amount of energy needed for reactants to collide successfully, which determines the reaction rate. Now, if you're wondering, how does the activation energy determine the reaction rate? Well, let me show you. Say we have, with that, we also have another activation energy, which is like that. Now, let's say we have a bunch of reactant particles over here, right? If these reactant particles are only a few will collide with enough energy that is equivalent to the activation energy when it's this high, but a lot more will collide, right, with a lower activation energy, and therefore we'll notice that we'll have more product when the activation energy is lower, because a lot more can get over this hill, as opposed to when the activation energy is higher. Here, only a few will probably be able to get over the energy hill. Okay, great. Now let's talk we'll take a little bit of a deeper look at collisions on our next slide. So continuing our discussion on collisions, very few molecules actually have enough, when they collide, have enough energy that is equal to or greater than the activation energy. Most of those collisions we'll see, as we see here, right, are going to have average energy, and even fewer have lower energy, with only a few that have high energy, right? And let's only focus on the blue line for now. Sorry, I should have just mentioned that too. Yeah, if we want to increase the amount of collisions, so the collisions will have enough energy equal to or greater than the activation energy, leading to more product, then there's two ways that we can do that. We can actually do that through one, which says right here, we can increase the temperature, or secondly, we can add a catalyst. Now let's take a look and see what happens when we increase the temperature. When we increase the temperature, we have less molecules here with the average energy, and we have even fewer particles here with lower energy, but we'll have more particles here that have energy that is equal to or greater than the activation energy. Right? Perfect. Secondly, we can add a catalyst, and when you add a catalyst, what that does is it decreases the activation energy. So therefore now, all of this here will be the fraction, all this here will be the fraction of particles with energy equal to or greater than the activation energy. Okay, wonderful. Let's actually move to our next slide now, and we'll take a look at an actual reaction. Okay. First question here, it's asking us, what type of reaction is this, exothermic or endothermic? As we see here, the enthalpy change is negative, so we know that heat is basically being released. So we go from a higher energy state to a lower energy state. So this will, we can firmly say that yes, this is a exothermic reaction. Now it's asking us, what would the transition state look like, right? Let's take a look at our reaction here. Okay, our reaction firstly is, here we have nitrous oxide reacting with nitric oxide to give us nitrogen and nitrogen dioxide. With the nitrous oxide going to the nitrogen gas, we see here that there's going to be a bond breakage between a nitrogen and an oxygen. And on the nitric oxide, we see here that because it's gained an oxygen, that there's going to be a bond forming between the oxygen and a nitrogen. Our transition state would look like the following. And this is, oh yeah, just NO here. Okay, great. Now let's just take a moment quickly here and discuss what we just wrote down.